Let's now talk about how dynamic tables work with MapReduce in YTsaurus. Typically, MapReduce operations are run against static tables. They are certain long-running batch tasks for OLAP. As an input, MapReduce gets one or more static tables. As an output, it also delivers one or more static tables, with the result of the processing. However, you can also use dynamic tables to run MapReduce operations. As an input, they are delivered in the same way as static ones. When it comes to the interface, there is no difference. Let's get back to our table, home/din/table, where we already have 5 rows. We'll now run a simple MapReduce operation against it. For starters, let's just run a merge. We are running the it-merge command, specify the input table, home/din/table, and the output 1, home/din/output. For the merge mode, we'll specify ordered. This means the rows will appear in the output table in the same order as they are in the static one. Let's run our operation. It's over now. What can we see in the output table? As expected, there are 5 rows. Let's now write another row to the dynamic table. For instance, we can add a row with key 100 and the value of 100. Let's run our merge operation again. This time, to the output to table. Let's open output to in the UI. We can see it has 6 rows. When it comes to dynamic tables, there is a pitfall when running MapReduce operations where a dynamic table is an input one. This is because a part of dynamic table data is in chunks, that is, it is physically dumped to the disk, while another part is still in the dynamic stores. Such data is stored in memory and is not yet dumped to the disk. By default, MapReduce operations typically see only chunked data. For the in-memory data to become available to such operations, one uses the enable_dynamic_store_read option. You can see it among the attributes of the source dynamic table. Let's open the Attributes tab and search for it by typing enabledin. We can see enable_dynamic_store_read is set to true. You might remember we did set it to true shortly after we started our webinar, right for the merge operation to run correctly. Let's see what happens if we disable this option. We'll unmount the table, specify the sync flag to wait until it is unmounted, and set enable_dynamic_store_read to false. Now we'll mount the table again and insert another value, say 101. After running merge to output 3, we'll see the output 3 table does not have the 101 value for key 101. Let's check it. We're opening output 3 in the UI, and indeed, we've still got 6 rows there. Thus, we need enable_dynamic_store_read so that all data, including the newest one, that was written to a dynamic table makes it to the input for MapReduce jobs. You can use dynamic tables not only as input, but also as output. If you run a MapReduce operation and specify a dynamic table as an output, all data the operation delivers as output will be either added to the dynamic table or fully overwrite what the table currently has, depending on the setting you specify. Let's look at it based on an example. I'll prepare a table with data. I'll create it. And I'll add some data to it, the data we will then be inserting into a dynamic table. I'm using it write table instead of it insert rows because insert rows means inserting data to dynamic tables, while write table means writing to static ones. Now I can read from home/din/data, which is a static table, using read table. I'll now try to insert the data to a dynamic table. For that, I'll also use the it-merge command. This is a very basic operation. In order to use the overwrite mode, I am specifying the append attribute within the path to the output table. I am also specifying the ordered mode, so that the rows get into the output table in the same order they appear in the source one. And let's run the operation. We can see there are issues because of certain access permissions. To learn more about enabling access to bulk insert, in our terms, this is writing to output tables, refer to our documentation. Now I'll just run a few commands to get this access back. Why does one even need this access? Because, historically, this feature was very easy to misuse. Some users just applied it accidentally, for instance, by using write to a dynamic table instead of insert. So we had to restrict it and made this feature available only to those who understand what they are doing and request it explicitly. We also have it covered in our documentation. In particular, you can learn how to disable this restriction for your cluster. For now, however, I will just grant this access manually. Let's try again. This time, everything is okay. Let's look at our dynamic table. Here we go. There are rows with keys 50 and 150 we got from the static table. We did it. Apart from running MapReduce, you can get dynamic tables from static ones by simply converting them. That is, you can prepare data as a static table, and then turn it into a dynamic one with a single command. For that, however, you need to create a static table in a specific way, namely, by providing it with a schema. You might remember that, when we were creating dynamic tables, we provided a table with a schema listing its key and value columns. Now we need to do the same for a static table. So, let's do it. I'm creating a table. And providing it with a schema through attributes. I will specify one key and one value column. Note that this schema is not enough. If you take a good look at a dynamic table schema in the UI, you will see it has the unique _keys attribute set to true. This means the system validates, at the schema level, that each key in the table has only one value. When it comes to static tables, even with a sorted schema, a single key may have multiple values. This is okay, and sometimes it might be handy. A database doesn't have to contain only unique keys. As for dynamic tables, however, this restriction applies. This is why, when creating a static table to convert to a dynamic one, we also must specify an attribute for unique keys in the schema. This is done through the unique _keys equals %true attribute added to the schema list. So, let's create a table and try to write something to it. First, however, let's check the unique _keys attribute is actually working and running the validation correctly. Let's try to write key 0 twice. I just did it, with two different values. I got an error saying key 0 is duplicate. The hash following 0 in the duplicate key line means this is the 0 value in the column with the 0 index. Let me fix this. I will change the value from 0 to 1 and write the data again. Now my table, that is called static, does have 2 rows. In the UI, we can see this is really a static table, and we can convert it to dynamic. For this, we'll use the altertable command. It altertable home/din/static. I am adding the dynamic flag, telling the system I want to convert my table to dynamic. Let's open our table in the UI and refresh the page. We can see it's been converted to dynamic, but we can't read any data from it because it is unmounted. So let's mount it. Let's get back to the UI, and we can see all data in this table. Can't yet see. Why can't we actually see it? Okay, after refreshing the page, we can. Well, this is a rule of thumb when using dynamic tables and, generally, databases. Do not forget about retries. If your query returned an error, just wait for a retry, and, most likely, you will get what you want after the second attempt. Well, jokes are half meant, so really, do not forget about retries when working in a production environment. You just can't avoid network errors at every point in time. So, we learned how to convert static tables to dynamic. Can we convert dynamic ones back to static? If they are sorted, then, normally, we cannot. Well, you can do that using merge operations by running them against a dynamic table. You will get a static one this way, but this will involve reading all data. In the meantime, altertable is a quick metadata level operation that does not physically work with data. It will just tell the system, at the master server level, that all relevant data now refers to a dynamic table. So, for sorted tables, the conversion is one-sided. If you use ordered tables that are basically queues, you can convert them to static and then back to dynamic. Since the format is totally compatible, the conversion works both ways. Let's now talk about dynamic table settings and features, and how you can actually configure such tables. Largely, you can manage the configuration through attributes. Every table has an Attributes tab that houses multiple key-value pairs. Most of those attributes are barely usable. Others are used for information purposes. For example, we have the data_weight attribute with a value of 25. This is the total logical amount of data the table contains. Another one, preload_state. refers to the tables that are loaded to memory and shows whether the table has been fully loaded. Here's another one, dynamic, that just tells us this table is dynamic. Some attributes have null as their values. This means they are heavy enough so as not to show them in the list. However, you can explicitly read their values. For example, let's read the tablet's attribute for home/din. Well, let's take home/din/table to just leave our previous static table in peace. For home/din/table, let's read the tablet's attribute value through the UI. To see the attribute value through the UI, you need to provide the path to the table and then type /@ and the attribute name. The tablet's attribute is a kind of dictionary that lists a lot of info referring to the table's tablets. You can read the value of any other attribute in the same way. For instance, you can learn the number of tables, 1, or you can learn the value of enable_dynamic_store_read. The one we mentioned before when talking about MapReduce. It is false, which is natural, as we recently set it to this value. Using attributes, you can configure various things for a table. We already talked about enable_dynamic_store_read. There are some other reconfigurations available. For instance, there is a setting to load the dynamic table data into memory. By default, a table with data chunks is stored on a disk, while only a small piece of data, newly written to the dynamic store, lies in the memory. You can tell the table to store all its data in the memory. This will not prevent the data from being securely stored as chunks on a disk. However, for efficient reading, all chunked data will be forcibly cached into memory. This is configured through an _memory_mode. I can set this attribute for the table. There are two options here, compressed and uncompressed. Compressed means storing compressed data in the memory. Uncompressed means the opposite. Storing compressed data requires less memory, but takes more time to access such data because it needs to be decompressed first. For uncompressed data, the trade-offs are the opposite. In our example, let's use compressed. The system does not allow us to set it, as you cannot change some attributes while the table is mounted. You need to unmount it first, that is, to switch it to the mode when you cannot write to or read from it. Let's just do it. Now that we've set the attribute, let's mount our table back and try to open it in the UI. Let's refresh the page. We can now see this data again, and it is now loaded from memory. We can even see the in-memory mode status, which says compressed. Our table works much faster now. You may have failed to notice that, but in fact, the page got refreshed a few milliseconds, if not hundreds of milliseconds. Faster than before, when it was not yet in the memory. What other settings do we have? A significant part of those are in the mount_config attribute. This attribute even has a dedicated tab in the UI. Currently, it is empty. Let me tell you which settings can be there. First, you can set till for a table. For instance, you may want to only store data for the last 7 days and delete any older data. For that, you need to specify a few attributes within mount_config. You can do it even without unmounting the table. I will now show you how these attributes may look like. For precise semantics, refer to our documentation. There is a dedicated section on till that tells you which attributes are used to configure it and what they mean. This is a rather rich model that enables expressing complex predicates with just a few attributes. For instance, let's assume you want to store all versions of all rows for the last 30 minutes, so that you could consistently read data for any point in time. At the same time, you can keep only the latest version for all rows that are from 30 minutes to 7 days old. to see the data written over the last 7 days. Finally, you don't need the data written prior to the last 7 days, so you just want it removed. The tool model will allow you to configure this using a few attributes. This is how you can roughly do it. I'll set the min_data_tool attribute to, say, 7 days. This will be 7 multiplied by 24 by 60 by 60 by 1000. This means 7 days converted to milliseconds. Now I'm heading to the UI, and here we go. This value is now in the Mount Config tab. To apply this value to the table, you need to run a specific command, remount table. Remount table does not make the data unavailable, it just applies the settings to the table and sends them to the nodes. By default, the settings only apply the master, so you need to use remount to send them to the table's nodes. Now, the settings have been applied. What other settings do we have? For instance, the compaction settings. Let's assume you need your table's data chunks compacted on a regular basis. You may need this, say, for removing old data in a more aggressive manner. This can be done with the auto_compaction_period attribute. I can set this period to 24 hours and run remount table again. This will guarantee that all chunks will be compacted, roughly, once in 24 hours. And if any data can be removed by tool, it will be removed. Let's refresh the page, and we'll see this attribute is also there. There are also auto-sharding settings that are managed by the tablet_balancer_config attribute. We can see that, by default, auto-sharding, or moving tablets automatically, is allowed for this table. You can also use this attribute to set the minimum and maximum tablet size, which the balancer will take into account. For precise semantics and the full list of attributes, refer to the auto-sharding section of our documentation. To simplify the auto-sharding process, you can use calculable columns. After sharding a table, you will typically want to evenly distribute the load across all shards. However, there are cases when the primary key in a table does not assume writing the data evenly, for instance, when it is a website URL. If this is what happens, the shard that maintains the rows starting with www, in case of sorting by primary key, will be highly overloaded. In the meantime, the shard that works with the rows that start with other letters will be idle, while you may want to route some load its way too. For such cases, we suggest using calculable columns. This actually converts a common primary key into a key starting with a data hash that you can specify. Let me show you how this works in practical terms and how the table will look like in the UI. I'll create a table. I will make it dynamic. This time, the schema will have 3 columns. I'll name the first one as hash and specify the unsigned 64-bit type for it. It will also have the sort order, since it is a key column. And there's another argument. We'll understand what it means soon. By specifying expression, we tell the system that the user won't explicitly specify the value for this column. Instead, it will be calculated based on others. Now we'll explicitly specify the key column with the type of our choice. And also the value column. Let's create the table, mount it, and insert a few values. I won't even specify the values. If you don't specify a value for a column, it will be null by default. I'm inserting 0, 1, then 2, and now I'll view the table in the UI. Now we've got the hash column that contains the hash of the key column, the one that has the meaningful data. And the table is sorted by hash. This way, the load on all shards will be more or less the same if you evenly split the table by the uint64 range, since every row will fall into a random shard by hash. We can see how it looks like in the table schema in the UI. Here is the hash column with an expression. This is a calculable expression. Typically, you can use hash for one or a few key columns. Finally, let's talk about replicated tables and how YTsaurus handles the cluster downtime. The tables we just talked about fully belong to a single cluster. When anything happens to it, such as issues, scheduled maintenance, or updates, the table will become unavailable. To avoid this, we have table replication. Typically, this works like this. We have a highly available cluster, the so-called metacluster. Apart from being highly available, it rarely has any updates. In some cases, it may be cross-data center or have various components in multiple locations, so that when one location is down, the cluster is still available. This cluster houses the replication queues and maintains the writing process. Apart from that, we've got a few standalone clusters on which the replica tables reside. These replica tables connect to a queue, and when a user writes data to a table, a cluster writes it to the queue and, probably, to one or more data tables. Replica tables may be both synchronous and asynchronous. When a user writes data, the data record gets into a queue and all synchronous replicas, and then gets copied to the asynchronous ones in the background mode. The system provides a guarantee for consistency. That is, if any asynchronous replica is currently unavailable, then, once it's back, all rows from the replication queue will get into it in the same order they were written into the queue. So, eventually, all replicas will have the same state. Moreover, if you have two synchronous replicas, it is guaranteed that their state is also the same. Let's discuss how you can configure such a scenario. If we have any time left, we'll also talk about the implementation details and what all replicas have the same state actually means. This is because, in a distributed system, one may hardly assume that. Looking ahead, the guarantee is as follows. If you try to read anything from the replicas by a timestamp that is already in the past, it is guaranteed that you will read the same thing from all replicas. Now let's look at how you can implement this. As we only have one cluster, it will also house our replicas, however. This does not differ much from the scenario when you have multiple clusters. In the latter case, you will just need to tell the clusters about one another's settings and specify the correct cluster name. First things first, Let's see what our demo cluster knows about others and how they are called. You can find this info in the sys/clusters map node. Here's a cluster named itdemo, and it has certain attributes that list the addresses by which you can communicate with the cluster components. There's also the cluster_connection attribute that tells us how to connect to the cluster. So, if you want your cluster A to communicate with cluster B, you just go to sys/clusters at the cluster A side and type B equals and the cluster_connection value for cluster B. In our case, the itdemo cluster can communicate with itself by default, so we can start using it as a backup cluster right away. Now let's configure a replicated table. A replicated table is technically a replication queue. It does not physically store any data. It is a standalone object that is very similar to a table but has another type, replicated_table. Apart from that, a replicated table must be a dynamic one. Oops, I forgot to give it a name. Okay, it's been created. Now let's look at it in the UI. There is no data for our replicated table, and this is fine, as we cannot read directly from it. Let's mount it. And try to write something into it. Curiously enough, it is a success. However, we still can't see any data, as the table does not have any replicas yet. Let's create them. To create a replica, you need to create two things. First, you need a table to which the data is going to be replicated. I'll just copy the schema to avoid typing it in once again. So first, you need a replica table. Second, you need a replica object that resides on the metacluster and tells the system where the replicated table will replicate its data. You can also do it using itCreate. We are creating a table_replica object. In the attributes first, let's specify the table to replicate. This is home/din/replicated. Second, which table the data will be replicated to. And finally, the cluster for replication. So, we created a replica, and now can even view something in the UI. Let's refresh the page, and here it is. The home/din/replica1 table. We can now go to our replica table. It is unmounted, let's fix it. The replica table currently has no data. Let's get back to the replicated table, and we can see our newly created replica has a red circle icon in the line that says state. This means it is disabled. Let's try to enable it. Here we can enable or disable the replica and toggle the replication mode, sync or async. If a replica is synchronous, the data will be written into it automatically. Right once a user writes data to the relevant replicated table, it will be literally committed within the same transaction. If the system fails to write data to at least one sync replica, it will also fail to do so to all others. We also have automatic mode switch. This is a feature that allows you to automatically switch replicas from the sync mode to async. You may need this to disable sync replicas for a cluster that is currently down. So, in a typical scenario, when you have 2 or 3 replication clusters, the system makes sure to fail the sync replicas over to other clusters when a cluster in question is shut down or unavailable for any reason. This way, the replication process is seamless and continuous. Let's enable our replica in the async mode and see whether the data will appear in the table. It's not there, and there might be various reasons for that. First, we forgot to do something important. To make a table a replica one rather than just a common table, you need to provide it with the upstream replica ID attribute. This will mean the table is linked to a replica object in the metacluster and can accept replicated data from the relevant table. Let's do this, and while we are at it, we can see our replication crashed. Here, we've got an error. In the top part of the table, there's now the Tablet Errors tab. Let's see what this error is. Write what I talked about. The home/din/replica1 table is not linked to any replica, while we tried to write data to it, saying that the replica ID is so and so. Let's fix this link. We need to go back to the replicated tables main tab, copy the replica ID, and fix the replica1 table to link it. For this, we need to unmount the replica and run alter table. As an argument, we'll specify upstream replica ID. Alter table is over, let's mount it back. And open replica1 to see whether the data is there. Not yet, the error is still there, let's wait a bit. There is a certain timeout, up to 60 seconds, in case the issue is serious. Misconfiguration is serious enough so as not to run regular retries. So this is why we need to wait. Wow, no errors. Let's see what happened to the replica, the data is there. Now let's try to write something else. For instance, row 1. We're unlucky this time. By default, if a table does not have any synchronous replicas, this is a misconfiguration, and we cannot write anything to such table. The only exception is when a table is empty. In this case, writing will be possible. So, let's make our replica synchronous. You can also do it through the UI. We've switched to the sync mode, and now we'll be able to write to the table. Not right away perhaps, but after some time, because there is some cache at various levels along the way. Well, we did it. Let's go to the replica table to see that the data is there. In the same way, you can create multiple replicas on different clusters for a single replicated table, and set those replicas to different modes. Typically, one replica would be sync, while others async. You can enable certain automated processes that will make sure that the sync replica is always on a cluster that is alive, so that the system is always available for reads. You can enable standalone reads from replica clusters. However, in this case, there might be issues with consistent reading. You can only read consistently from a sync replica, while for an async one, the data you read will typically lag for a few seconds. You can also read directly from the metacluster that will find a synchronous replica and point you to it. In the latter case, reading will always be consistent. Bottom line, such a scenario always allows for inconsistent reads, while consistent reads, as well as writes, are only possible when the metacluster is alive. This means full availability for reading if you are fine with some inconsistencies or lags, which is anyway better than a table that only resides on a single cluster and becomes unavailable every time this cluster is down. Well, this is roughly how the replicated tables work. And this concludes our webinar. I hope I managed to provide a comprehensive overview of our system, and you will be interested in further discovering its features. Feel free to check out our documentation and send your questions to our community chat. We'll be happy to answer them. If you don't find anything you need in the documentation, reach out to us and we will try to add more info on it. Come and use YTsaurus, and we'll be there to help.